All right, so for these next couple of lectures, we're going to talk about one-dimensional kinematics, and that's essentially just how an object or particle moves in just a horizontal or vertical direction. So we're not thinking about like any sort of weird two or three-dimensional motion yet. We're just going to talk about what's happening on essentially like a line plot in regards to motion. So just a little bit of history to sort of set the scene, so to speak. What really got the mathematics of motion and kinematics set up and going was actually just humans' natural curiosity of just what's going on in the sky and where planets and stars are. So we can start just by talking about Aristotle, who proposed a geocentric model of the solar system. That was an incorrect model where he put the Earth at the center of the solar system and everything revolving around it. Although it was incorrect, it was a pretty good idea. I mean, given the time and everything and how he reasoned through it, it was the best he could have done. Galileo came along much later, and he developed the heliocentric model, so he correctly put the sun in the middle of the solar system and had the planets go around it. He also had access to a little more technology than Aristotle had and a little more advanced mathematics. But really what solidified motion was essentially Newton, who was a powerhouse. He essentially invented calculus. So that allowed for a lot of very intricate calculations in regards to what the planets and stars are doing in the night sky. So essentially, we can take motion and break it down into 4 different types. Essentially, this fundamental definition of motion that we're dealing with is a change in an object's position with time. So that's helpful to think about what's going on over some length of time. We're going to use that idea later. So the path along which this moves, so the path is the trajectory. Okay, so anytime I want to talk about a particle's trajectory, I'm essentially just talking about what that particle's doing in between these points of time and space. So there's 4 different types of this motion we're talking about. Translational motion, where just some object is moving side to side, up, down, or some combination thereof. There's projectile motion, so this is a combination thereof, where we've got some sideways motion and we have some vertical motion happening at the same time. So you can imagine you'd have to keep track of what the ball's doing in the horizontal direction, and you'd have to keep track of what the ball's doing in the vertical direction. Both of these directions have things going on in them in projectile motion. Circular motion and rotational motion, they're similar, but you can think about circular motion as in a person, maybe a person in this seat here. You can think about their trajectory around the edge of the circle, whereas with rotational motion, the whole object is spinning. So with the circular motion on a Ferris wheel, we can actually pinpoint that person and watch them travel some trajectory, whereas rotational motion is more just like this spinning point particle or spinning blob. So the way we can talk about motion is with simply a motion diagram. And essentially what this is it's kind of like taking a bunch of snapshots of motion with a camera at equally spaced intervals. So you can see here we've got 5 different examples. You got this stationary ball on the ground. So the point here is that it's stationary. So at t=0 seconds, so right when the motion starts, the ball is sitting in that spot. After 1 second, the ball is still sitting in that spot. 10 seconds, the ball is still sitting in that spot. So the idea is that this is a very boring series of pictures because the ball is in the same place when we overlay all these pictures. Now, if something is traveling at a constant speed, as you can see here with the skateboarder, after every second, it's the same distance. Okay, so this is movement with a constant speed. And that's really easy to think about. It's just, it's almost like a copy-paste, equally spaced images across the screen. With some more of these, you can see that this runner is speeding up because her pictures are grouped together at the beginning, so she's getting less distance between those pictures. But then they start spreading out. So the distance between here and here are very different. And that indicates that she's speeding up. Now, the opposite, we can see that too. We can see the speed of something decrease, like this car. And over here, near the end of this time frame, they're getting closer together, which means they're covering less distance here at the end than they were at the beginning. So that's an indication that this object is slowing down. And then we could have an example of 2D motion, which we'll save that for later in the course. But you can see, like here, we have constant horizontal motion, so they're all equally spaced horizontally, but then we have some changes vertically. So it looks like if we just look at what's going on in the vertical, they're moving up and down all these pictures. So clearly there's like some speeding up, there's some slowing down, and then a reversing direction. So one direction is pretty complicated, while the horizontal direction is pretty standard, just constant speed. So instead of drawing all these complicated pictures for each problem that we're going to do, or each problem we're going to talk about, what we can do is simply just talk about, there we go. We can simply just talk about these translational diagrams as particle models. Oops. So instead of drawing out all these complicated pictures, we're just going to represent an object just as a point. So all of these will become dots, kind of like the basketball on the bottom. But there's some things you can't represent as a point particle. Like if you wanted to talk about a rotating gear, but you represented the gear as a point particle, well, then you essentially delete the rotation. Yeah, so the idea here is that this only works for an object where the shape doesn't affect the motion. So let's see, let's move on to position and time. With position, we can take formal position measurements if we lay a coordinate grid across the motion, like our motion diagram. So the origin of a coordinate system, or our coordinate grid, we can put the origin anywhere we want to. This is like time equals 0, distance equals 0. This is like our home base, and it's arbitrary. We can assign wherever we want it to be. Oops. Let me fix this. There we go. So in that case, yeah, so what's happening? My apologies. As I was saying, the origin. Yeah, that's our home base. We can do the same thing with time, which is here next. Time is also a coordinate system. And it's just an arbitrary time. We set it t equals 0, so it could be 10 a.m. That's our t equals 0. Then everything is measured relative to that time. 9 a.m. would be -1 hour, 11 a.m. would be +1 hour. It's just an arbitrary point, which is an important thing to remember. We get to assign it. And then any motion occurring before t equals 0, we usually represent as negative time. So that's also important. Now, the thing with our position coordinate system and our time coordinate system, if we have 20 people watching an object, they can all define a different origin and set up their own coordinate system. We could have 20 different coordinate systems for position and 20 different coordinate systems for time. But when they measure those changes in position over time, everyone's going to come up with the same measurements. If some ball rolls across the ground for 2 feet, in 2 seconds, everyone's going to measure that same 2 feet in 2 seconds, even though we have 20 different coordinate systems going on. So this is important, and I'll show a more thorough example a little bit later. Now let's talk about one-dimensional vectors. So a position, all these positions we're talking about, that's actually a vector quantity. And that means it has a magnitude and a direction. So that's actually a consequence of adding a coordinate system. As soon as we add a coordinate system, we can start talking about these vectors. So do keep that in mind, that when we throw down a coordinate system, that gives us a means to actually start calculating vectors. So a scalar quantity is essentially, it's kind of like the opposite of a vector. It has a value such as temperature, but it doesn't have an associated direction. So I could say, oh, you know, I'm 10 meters to the west of my house. Well, if my house is the origin, that'd be, you know, plus 10 meters minus 10 meters, some sort of direction away from a coordinate or away from an origin. But it doesn't make sense to say, oh, well, it's 30 degrees in that direction. So that's why some things are scalars. They just have a magnitude. They just have a value. Then a direction wouldn't make sense. So we actually indicate these position vectors as generally R. So it's an R with the vector hat. So this little guy is a vector hat. Okay, so it doesn't have to be a position that's represented as a vector. There's several other things. Velocities are vectors. There's some sort magnetic fields are vectors, or can be represented as vectors. So there's things. Torque can be represented as a vector. All you have to know is that if it's a vector and it's got a vector hat on it, that means there's some sort of like position associated with it and a magnitude. Our positions are measured always from an origin. So vectors, when I say that they're measured from an origin, essentially they are just represented graphically by an arrow. Not the arrow over the variable, but an actual arrow in the coordinate system. Okay, so the direction of the arrow represents the direction of the position from the origin. Okay, so the direction of the arrow represents the direction of the position from the origin. That's important. Okay, so the amount of distance, so how far away we are from the origin, is represented by the length of the arrow. So let's take a look at this example here. So we have this slightly longer vector on the bottom right. We've defined anything going to the right or to the east as positive x direction, x because it's horizontal. If we were doing vertical, we'd call it the y direction. Okay, so we have positive move or a positive distance over here in the x direction. Now, if we started going west or to the left, that's the complete opposite direction. So now we have a negative distance. So that's why that negative is in front of the vector. You'll notice that both of these are measured from the origin. Okay, our origin is 0 meters. If we were talking about things in time, then we would have 0 seconds as our origin. So let's just look at a quick example. So suppose Sam starts at his house, which is the origin, okay? So he's gonna start at his house, okay? Okay, he starts at his house and he walks 100 meters to the east, arriving at the post office. So that would look like this, okay? So there's this new vector, it's positive, he's moving in the positive direction to the east, and it's got a length of 100 meters, and he just went to the post office. Now, shortly after, he walks negative 150 meters to the coffee shop. Now, notice it says he walks negative 150 meters. If we said he walked 150 meters, we wouldn't know which direction. So that's why we always have to assume that the plus or negative sign on a value is going to tell us which direction this motion is happening. Okay, so he's moving 150 meters west to the coffee shop near his home. So that means he's going back, okay, he's going back. Well, there's 100 meters or negative 100 meters, but then he goes 50 meters more to get to the coffee shop. Now, right, okay, so this second note, this is exactly what I said. The direction tells, or the sign out front tells us which direction this movement is. Now, next question. What about his total distance traveled versus his total displacement? Yeah. Okay. So there's a distance. There's a difference here. Sorry. So the total distance traveled doesn't really care about the direction you're going. It just cares how many steps you've taken, pretty much. So here we can think about it as in he's moving 100 meters to the east, but then he's moving negative 150 meters to the west. Now, I don't care that it's positive or negative. I just want the magnitude. So you'll see here, I've included these absolute value signs, and that just means if you've ever come across this in a math course, the absolute values, you just take the magnitude of it, whether it's positive or negative. So the magnitude of this is 150 meters. So these are absolute value symbols. So if we add these two things together, it turns out he walked a total of 250 meters. Okay, well, that's his total distance, but now what about his total displacement? And the question is, what do I mean by displacement? So the idea is essentially, let's see, do I have it in a sentence here? Yes, we can look right here. So the idea of displacement is how far you are away from the origin, okay? So now he's not that far away from the origin. He's right there, negative 50 meters away. So even though he's covered a lot of distance, his final displacement is not that big, okay? So the way we can calculate this is essentially it's the difference between the starting point and the ending point. And this is the particle's trajectory is irrelevant. We just want to know, where did it start? Where did it end? The difference between these two things, that is your displacement. Okay, now you can see here, now this down here gets a little tricky. Okay, we talk about displacement and it's represented as a delta R. Now delta R really just means a difference. It's this final thing minus this initial thing. And we write it out right here. I've got it in yellow, that means it's important. So we have this final, our final, the final distance minus the initial distance will give us our final displacement, or give us Sam's final displacement. Now, delta R is a displacement vector, distance from origin, but just Ri and Rf, those are position vectors. Okay, so they're less important. That just tells us where his initial position was, his final position was, but the displacement is always the difference between the two. So that's important to remember. So let's look at this. Clearly, I mean, I said it on the last slide, Sam's displacement is just where he ends up over here, negative 50 meters from his house at the coffee shop. Now let's think about this for a second. Sam started at the origin, which is his home. Okay, so if he's already on the origin, his initial position vector, it has to be 0. It's the position is how far you are away from the origin, but he's on the origin, so his initial position vector 0, and then this final where he ended up, that's just negative 50 meters from his house, or negative 50 meters from the origin. So notice that the trip to the post office doesn't even show up in his final displacement or total displacement. There's no indication that he ever actually visited the post office. So it turns out that your displacement doesn't really care about what trajectory you take, how you get there. It just wants to know your final minus your initial. And here's the math. If you need to see it, so we plug in the negative 50 for the final position vector, 0 because he started on the origin for the initial, and then when you do that subtraction, you just get negative 50 meters. I'm going to make sure I don't skip anything. So in that previous example, we did final, the very endpoint minus the initial, but we can actually do smaller pieces, right? We can actually calculate a displacement vector for the first leg of his trip. We can also do it for the second leg of his trip, where he actually goes back toward the coffee shop. So let's think about adding all these up. So let's add his first displacement vector. Well, it's 0 because he's still at his house. Okay, so you'll notice down here in our equation that we still have the original definition, but we're going to actually sum all these intermediate pieces, okay? And it turns out all these chunks added together, it's just going to equal the same thing as before, where it's the final minus the initial. So the first piece we know is 0, because he's at the origin already. Now, his second piece is when he leaves his house and goes to the post office. So he's heading over here. Now, that we know is 100 meters, okay? His displacement now is 100 meters, positive 100 meters from the origin. Okay, so we have the original 0 meters included. There says positive 100 meters from this initial displacement. Now, remember, it's position versus displacement. So this is our displacement vector. He's been displaced from the origin 100 meters. Okay, now he's going to come back. Now he's going to be displaced from the post office. Okay, so each time we're kind of updating our origin. Now he's going to be displaced from the post office back to the coffee shop. Okay, now that displacement from the previous position is going to be negative 150 meters because we're heading in the other direction. And when you keep updating your origin and keep calculating these little displacement chunks, okay, you can add them up, and it turns out we do, in fact, get the same thing that we did when we just calculated the final minus initial position vectors. Now we can think about changes in time as well. We have, instances where we can measure a specific time when an event happens, but we can also measure how things change over a time interval. Just like with a displacement vector for a position where there's a difference, we can do the same thing with time. So we can have two different times, T1 and T2. They may be assigned to two different positions of the particle in motion. So at T1, the particle's here, T2, the particle's here. The two values are arbitrary. They're measured from an arbitrary origin that we get to choose. But when we find the difference, that delta T, that is not arbitrary because that length is going to be invariant no matter when we decide to start timing. If we have our interval set up correctly, that delta T will be the same no matter who's measuring it. So this delta T here, this T2 minus T1, well, it represents the amount of time taken for an object to move from position 1 to position 2. So R1, T1, to R2, T2. Kind of sounds like R2, T2. Did not mean to do that. Now here's that important point that I was making earlier. It doesn't matter who is doing the measurement or where they're doing it from. If they have a solid coordinate system set up, everyone's math is going to match, okay? So here, let's take a look at this. So suppose a group of observers detect an object moving from an initial position, Ri, to a final position, but they all use a different coordinate system. Furthermore, all observers recorded the time of these positions as Ti and Tf, but they all started their stopwatches at different times before the motion started. Okay, so nonetheless, even though that Ri, Rf, Ti, and Tf are different for each observer, delta R and delta T are independent of the coordinate systems. Now let's take a look at this picture. So we have two people. We have someone over here at the coffee shop. Now notice they're offset from our axis just so you can see the vectors better. So remember, the position vectors are just measured from the origin. Okay, so here's person 1, here's person 2. So person 1, his origin is at the coffee shop. And you'll notice his RF and RI are very different. So the initial positions, this is them watching Sam. I don't know if I mentioned that, but we're still looking at what Sam's doing. So Sam did start at his home, and his final location is over here at the coffee shop. So if they're watching Sam, notice that even though their initial positions are pointing in opposite directions. So this one is positive, whereas person number 2's is pointing in a negative direction. They're still pointing to the same place, even though that these two people have two different origins. Their initial positions of where Sam is, that stays the same. And then you'll notice that their final positions, even though their final position vectors come from two different origins, they're pointing at the same place where Sam ends up. Now, if you think about the difference between, for both of these people, the difference between RF and RI, and you do that subtraction, in both cases, you'll notice that you get delta R here. So both of these people, if they take their independent position vectors and subtract them, they're still going to get delta R right here. Both people get the same thing. And if we look at delta T, see here you notice that even though they start their stopwatches at two different times, when they measure the initial time here of where Sam's at his home and then the final time where he shows up at the coffee shop, this distance, this delta T, also the same, no matter when they started their stopwatch. So that's important to keep in mind later on in the course when we start comparing how things move in different reference frames. So let's quickly talk about speed versus velocity. And then we can actually start using the delta R and the delta T to talk about how fast Sam is doing these errands. So in general, a common way to think about fastness or slowness of an object is just to consider the average speed, and that's just the total distance traveled, how many steps you took, how many feet you went, how many meters you went, divided by how long it took you to get there. So again, this is one of those things where it doesn't care about direction, it just wants to know your steps. It wants to look at your pedometer when you're done at the end of the day. So the problem here is there's no directional information. So average speed, well, that's just a scalar. It has a magnitude to tell you how many steps you took, how long it took you to do it, but can't tell you where you ended up. So if we wanted to require directional information, or if we needed it, then we need to calculate the average velocity. Okay, so for a velocity, it reports, or a velocity requires both a magnitude and a direction. So you'll notice the definition of velocity, it's got this displacement vector in it, and that displacement vector has position and direction information. So all that happens here when we calculate a velocity is we take that displacement vector, and essentially, if we break up this fraction, which is totally fine, really we're just multiplying this vector value by some number out front. It's just a scaling factor. So that's allowing us to take our distance, but then we modify it. We modify its length for it to represent a velocity instead of a distance. So notice that the average velocity vector, it points in the same direction as the distance. A longer velocity vector, so if it's a really long arrow, that means it's moving really fast. If it's a short arrow, it's going to be a slower motion. So let's go back to the SAM problem revisited again, and let's actually calculate his average speed and average velocity. Okay, so suppose Sam starts at his home, the origin, just like we talked about, and same thing, he walks to the east, but he does it in 100 seconds. So now we have a distance and we have a time. So we can actually start talking about a rate here. Okay, so I'm gonna say we have some sort of position and we have time. Okay, and he arrives at the post office again. He stays here for 3 minutes before he heads west back to the coffee shop, just like in the previous example. And that segment was actually completed in 200 seconds. So what was his average speed and what was his average velocity? Well, remember, average speed is just the total distance traveled over how long it took him to do it. So you'll notice here, we have in this first chunk of numbers in the numerator and denominator, we have his first 100 meters to the post office, and that took him 100 seconds. Now the second one I've marked in red, and that's because he didn't go anywhere for 3 whole minutes because he was at the post office. So I've marked it here So that's including the time that elapsed, but no motion was happening. So that's going to give us a 0 up in the numerator, and then that time's still ticking, so it goes in the denominator. Again, as he walks back to the coffee shop, that's a negative distance, but since we're talking about total distance traveled, that's going to be a magnitude, so essentially positive 150 meters. When we add everything up across the top, he's traveled a total of 250 meters, and he's done it in 400 seconds. So this is our total distance, and this is our total time. And then it turns out his average speed is 0.52 meters per second. You'll notice that tells us how fast he went, but we have no idea where he is. We know, because we've done the previous problem, that he's in the negative x direction. He's to the west of his house, so he's somewhere in the negative x direction, but that's not even reflected here in the average speed. Now, if we do the same thing with the average velocity, okay, now we know his position, the final minus the initial, same with time, final time minus initial time. Okay, we don't have to include any intermediate steps. So you'll notice that the delta R is the same as the previous problem, and our time's going to be the same thing, just total amount of time it took him to get from TI to TF or RI to RF. Same amount of time. And look here, we actually have a negative average velocity. So that means on average, out of that whole scenario, he tended to be moving in the negative direction toward the left or toward the west, toward the coffee shop. I tend to naturally gravitate toward the coffee shops myself. So we've got this definition of average velocity, average speed, but now let's look at just some very simple examples of this, and we'll call it uniform motion. And that's essentially just straight line motion with equal displacement occurring in equal time intervals. Equal time intervals. And then the question is, well, what does that mean? Well, all that means is velocity is not changing. Okay, so if you're walking at 2 meters per second and you continue to walk at 2 meters per second in the same direction, no changes, no turns, well, that's just uniform motion. This is really useful for like satellites like Voyager 1, which is outside the solar system and is just trucking at a constant speed. It's a situation like that you should be thinking of. So let's consider this plot of horizontal distance. Okay, so on the y-axis, I know it is weird because it's up and down, but this is our horizontal position. So okay, so a positive will be movement to the east, a negative value will be movement to the west. But now, because we're graphing it, we can actually think about how this changes over time. So you can see as we step through, just like this says here, essentially the same amount of distance is added for each time interval. So as time ticks on, we keep adding a chunk of distance to where we're at. So we start at 1 meter, you can see here, but after 1 second, we've added positive 2 meters to our initial position. So now we're at 3 meters. Okay, well, that was a movement to the east. And if you look at this next second, we add 2 more meters positive. So that's going to be more to the right or to the east. And then again, so after each second, we're essentially just adding the same amount every time. And that is uniform motion graphically represented. So just some things you should keep in mind with these uniform motion plots and just these position versus time plots in general. Steeper slopes correspond to faster speeds, because that just means this says more speed. I think it'd be better to say more distance is being added in less time. So you can imagine if this is distance, time. Well, if we're barely adding distance over time, we're not gonna have a big slope. But now if we're adding 10 meters every second to where we're at, we're gonna have a much larger plot for a much steeper slope. Fast and slow. Negative slopes correspond to negative velocities. So that means if we have, we start at the origin, but then all of a sudden we have a negative slope, that means we're moving in the west direction or to the left on a plot. So this would be the negative direction. And then something that's important to remember is the slope is a ratio of intervals, not coordinates. So it's always the change in position over change in time, not just some position value divided by some t value. So now let's actually take this definition, essentially of the slope of our graph, rise over run. Let's take it and tweak it into a kinematic equation that's going to be useful, that we can keep in our back pocket and then use later for other calculations. So suppose we want an equation that would allow us to determine, this is what we want, this is our output. We want to determine an object's position at some point in time. So if we say, what is this object doing, or where is this object at in 10 seconds? Okay, we want some equation that we can just have handy, where you can just plug in 10 seconds and it will tell us what's going on. So the object's position at some time t. Oh, wow. There we go. Now, we are going to assume that this is a uniform motion, so v is not changing. Later on, we'll assume that v is changing, and that'll make the math a little funky, but it's still totally manageable. Okay, so let's take our initial definition. Now I'm going to write it as delta x, since we've constrained it to just horizontal motion right now. But you can change it to delta r, delta y if we're dealing with something moving up and down. So we know our average velocity is just delta x over delta t. Okay, that's the definition we've had for several slides now. Well, let's unpack that. So we know that's a final minus initial for both of these things. Now the denominator, we don't have to do that. We can just leave it as a delta t. I just wanted to write this other step to remind you that both of these are deltas with a final minus initial. So if we leave that, what we can do is just say, well, v average just equals the stuff. That's why I have it both in green. So if we set those two things equal to each other, we can solve for that xf, that final position. Now when we do that, we get a much cleaner and more useful equation out of that slope definition. And we can rewrite it. It's the same thing. I've just highlighted it here and took out the v average. Just as long as you remember that this is for constant velocity where v isn't changing at all, you can ignore the average. It makes it easier to read. So this is our first kinematic equation that we're going to use. It turns out it's super handy. So if you pay attention, hopefully you'll notice that this should look familiar. So it turns out, let me get rid of my notes here. There we go. So it turns out that this is just the slope equation, like the linear equation, y equals mx plus b. And I've color coded the pieces and how they correspond to each other. Your xf, your final position, well, that's just the your output, like your equation when you solve it, just like with a linear equation from like back in middle school. And that's what we want. We want to know the y value. We want to know the final position. Well, your initial position xi, that's just your y-intercept. So where does it start at on the plot? V, well, you can see here from this previous definition right here, well, v is just your rise over run. That's your slope. So just like m in the regular linear equation. And then delta t, well, that's just your x-coordinate. At what time, so we're, instead of saying at what x does y happen, or at this x, this is what y is, now we're just saying at this t, this is our final x. So that's just your input x-coordinate. And you can see that from the plot on the previous slide that I have here. So here, our b value, b or initial position, is right here, is our y-intercept. Our slope, well, that's just the rise over run, delta x over delta t is just 2 meters per second. Here's our slope. And then notice we're just plugging in t's instead of x's. And what comes out, so our x final is just our final y value. So you can think about this uniform motion just like linear problems from like back in middle school, high school. All right, so let's put all of this together. Okay, so Bob leaves home in Chicago at 9 a.m. and he travels east at a steady 60 miles per hour. Okay, now Susan, who's already 400 miles to the east in Pittsburgh, well, she leaves at the same time. Okay, so their initial times are the same. She leaves at the same time, but she travels west at a steady 40 miles per hour. So we know she's going to be going negative 40 miles per hour. She's going west. So where do they meet for lunch? Now remember from our very first lecture when I was going over the course material, there's 4 steps that you should use, to think about when you're doing these problems. So the first 2 are model and visualize. So let's do that. We can model this, just draw a picture and visualize it. And then we start dumping in information that we have already. Okay, so we know over here at t equals 0, or yeah, at t equals 0 and at position 0. So we're using Bob's position here, Chicago, as the initial position and the origin. So here at Chicago, it's 0. His distance is 0. Well, we know his initial position. We know his velocity because it's steady. What is it? A steady 60 miles per hour. Well, and we know that this is the initial time, and we can say that it's t naught equals 0 because we can define it however we want to. You'll notice up here these individual velocities. They're uniform. They're all the same length, so we know that the velocity is not changing, so it's uniform motion. Now we know the similar stuff about Susan. We know her initial position is 400 meters east. We know her velocity, negative 40, and we know that her initial starting time was also t equals 0 because they started at the same time, and we get to decide that that is t equals 0. Now we know at some later time, we don't know what it is, but we know at t1, we know that they are going to meet because they have to be occupying the same point at the same t1. Now, we still know their velocities here because it's steady. It's either they're traveling this velocity or it's 0. And we also want to know, see, we don't know this though. We don't know these final positions. So we don't know x1 of Bob's, and we don't know x1 of Susan's. So that's a bit of a problem. This is the stuff in the middle that we're not sure about. Okay, so let me get rid of these notes I've made. Okay, so here we can, since we've identified what we know, where we know it, we can actually just write in these values. We know initial positions, and we know velocities, and we know t naught. The only thing we don't know is just essentially this relationship here. We don't know at what time they are at x1. We do know that their x1, Bob's x1 and Susan's x1 have to equal each other. But if we do find out what time that is, we don't care. We want to know where they meet for lunch, not when. So that's what we're after. We're after the where they meet for lunch. So let's set this up in these linear equations that we've been dealing with. Okay, so Bob's initial position, 0. He's already at the origin that we get to pick. Okay, so we said it was Chicago. T1, that's going to give us, if we plug in T1, that's going to give us his position at x1, even though we don't know those yet. We just know that if we put t1 there, x1 comes out of the equation. Same thing for Susan. She's already 400 miles away. She's traveling a negative, notice the negative, she's traveling in the negative direction. If we plug in t1 into her linear equation, we don't know what it is, but we do know that her x1 position is going to come out. Now here's how the whole crux of the problem works. We know that x1 is the same for both of them. Okay, so this is important. Since their final positions equal each other, we can take these two equations and set them equal to each other. So you'll notice Bob's equation is over here, and Susan's equation is over here. Now notice what we have. We have one t1 in this equation. So we can actually solve for it. We can just do some algebra, and it turns out the when they meet for lunch is in 4 hours. Okay, now the question is, okay, well, they meet in 4 hours, but where is that? So what we can do is we can take that 4 hours and then plug it back into one of our original equations. So that 4 hours can go back in here somewhere. You see how it's a bit circular? So it's one of those like problems from like back in 9th grade where you have two equations, you solve one, and you take that and plug it back into the other one, that kind of thing. So we can plug this t into either one of them. We know it's going to give us the same answer. But since Bob's is easier, there's a 0 in there, we'll just plug it back into Bob's. And it turns out they're going to meet at positive 240 miles away from Chicago. Now, if we plotted this, really what we're finding is that they're going to meet where these two linear graphs intersect, because this is their t1. They both have the same t1, and that means they both have the same x1. And you'll notice on the plot here, all of these values, all of our knowns, you can find in the plot. Okay, so we have, let's see, Bob's initial position. We know it's 0. This is on the y-axis. We know Susan's initial position was 400 miles away, and we know their speeds, right? So their speeds are going to be represented by the slopes of these lines. And now anywhere where there's an intersection, that's at the time and the place where those two things are essentially occupying the same space. So this right here is a really good relationship to think about. If you know that you're dealing with uniform motion and you know these parameters, you can sometimes plot it, and then you can see if there's any sort of interactions. And this relationship we could do without even knowing any of the math or doing any of the algebra. All right, so I'm running a little short on time, but given that my last video was a little short, I may go over just 1 or 2 minutes this time, so bear with me. With the uniform motion, it's okay. It only gets us so far. Like I said right here, the average velocity, it's only useful when it's only so useful when an object's velocity is changing. Okay, so we've been talking about what happens when an velocity does change, and then how could we find a velocity from position if the velocity is always changing, or if the position is doing really weird things? You remember all the previous plots, the position versus time graph, they were all straight lines. But now what if it was a not so straight line? So imagine this green line here. If we wanted to know from this position versus time sketch, if we wanted to know what the velocity was at t equals 2, well, it would kind of be hard to use the average, right? So let's see, I think I say here, yeah, let's see, let's go through these bullets, and while we're thinking about getting the velocity t equals, or t2 here. So with this changing velocity, we want to know the instantaneous velocity, right? So what is the velocity right when t2 happens? So this is essentially the speed and direction at a particular instant in time, not over an interval. So of course we could apply the definition of average velocity. Okay, so we're here. We could just apply the definition of the average velocity, right? We could say, well, you know, we could take x3 minus x1 over t3 minus t1. That would give us this orange line here, but it would also assume that it's linear. Well, it's not. You can see if we were to do this calculation, we're going to get some velocity up here. It's going to be offset. It's not going to be the real true velocity at t2, but we could get a close approximation. So now what we can do is essentially we can make this interval smaller. So what if t1 and t3 were really close to t2? So what if we brought these in? And if you remember your calculus, you know where this is going. So essentially, if we said, okay, our delta t, so remember this is delta x, delta t. So what if in the limit where we make our delta t really small and just bring the t1 and t3 closer together? Well, maybe we can get it so close that we essentially get an instantaneous measurement of velocity as we sandwich t2. And that's exactly what we're doing here. And this is just the derivative. And I'm sure some of you have dealt with these in calculus. If you've taken it, I think you do because it's a prereq. So hopefully everyone's had calculus. And essentially, the instantaneous velocity is just the slope of a line tangent to the x versus t plot. Okay, so if we let this happen, if we let t's t1 and t3 get close together, we'll eventually get a tangent line that touches at just one point, and that's the slope that we want. This does bring up an interesting point. You can see that the slope I've drawn is really close to the average that we thought about doing before. Sometimes you can actually, sometimes the average will get close. I think that is worth noting. Sometimes the AVG is close. But if you're dealing with something that's like crazy changes, like, I don't know, a rocket or something, you'll want to calculate it with calculus rather than just trying to do a small interval of time. So one more thing to think about with instantaneous velocity, and then we'll finish up. So if you know information about an object's velocity, but not its position, so we're going backwards. The last one was we know position, what about its velocity? Now we're thinking about we know its velocity, what about its position? Okay? So what we can do is we can think about, okay, if we know the initial position, okay, we can actually add up little changes, little displacements to get the final position. Okay, so we can start with initial position. Actually, I think I will zoom in for this. There we go. So we can think about the initial position, xi, plus little chunks. Okay, so we're going to add these little chunks. But wait. We don't know anything about the position, but we do know velocity versus time. Okay, so now we don't have to worry about the fact we don't already know position. So let's use this definition here, and we can rewrite the above equation. Okay, so we can replace the delta xk with just little chunks of average velocity. So the little average velocities at different times multiplied by those time intervals. Okay, so this is really just a substitution. And then if you're studious, you'll know like, oh wait, that's some constant out front with a delta t, and we're summing over all of them. Well, if we let our intervals get small, well, that just becomes an interval, right? So here's our definition of integral. So all this is essentially, if we know the velocity but want to go backwards to position information, if we know our initial position, all we have to do is just integrate across the velocity that we know. And that actually becomes our position. So it'll update that initial position to exactly where that final position needs to be. And that would be over some time interval. So essentially, this is the xi, so the initial position, plus the area under the velocity versus time graph. And then the area under the curve is just an integral. So you remember this from calculus, I hope. So instead of a delta x, we just have a delta t. And instead of a f of x, we're just going to have some velocity plot. And then everything else is the same. It's just an integration. So that's how we can work backwards from velocity to get to position. Ooh. Okay, so just to summarize quickly, as you work on building intuition about motion, you need to move back and forth between these 4 different representations. So a motion diagram, so the picture version, position versus time, so x versus t, and then velocity versus time, v versus t. Okay, and you'll also need to be able to read word descriptions and sort of convert between these 4 representations. So hopefully by the end of these couple of lectures, you'll be able to sketch motion diagrams, sketch position graphs, sketch velocity graphs, and then interpret all 3 of these. So I will stop there. I apologize for going over just a little bit, and we will continue this conversation in the next lecture where we're actually going to add acceleration. So essentially talking about when the velocity is changing and it's no longer uniform motion.